Hello, my name is Ryther, and I will be talking about our recent progress in predicting adsorption isotherms in metal organic frameworks, also known as MOFs, using deep learning algorithms. MOFs are a class of nanoporous crystal comprised of organic linkers connecting metal nodes and forming a huge variety of structures. MOFs are interesting for a lot of reasons, but are particularly good at retaining gases in their pores. This is due in part to large internal surface areas and crystallinity, but most importantly to their tunability. This tunability arises directly from the modular nature of MOF construction. Different metals and linkers can be used to fit certain adsorbates. The problem with this modularity, however, is there are often too many combinations to test. So how can we efficiently screen MOFs for new and existing adsorption applications? A general method for screening MOFs is to measure isotherms in a large number of structures, derive the relevant performance metrics, and select the top performers for further analysis. The more MOFs we can screen, the more likely we are to identify the best ones. So we can do this screening experimentally, but this is expensive and can take days to weeks for a single MOF. We can also calculate adsorption isotherms using Monte Carlo simulations, but this requires supercomputing resources and still takes hours to days. However, a machine learning model, once it is trained, can make accurate predictions of adsorption isotherms in fractions of a second on a laptop or phone. So our goal is to replace certain molecular simulations with predictions from machine learning models. This means we train our model on simulated data to predict future simulation results. Previous studies have focused on making predictions in new MOFs only, but what if you want to screen new adsorbates, operating conditions, and MOFs simultaneously? Our goal with this project was to develop a model that can do this. So we train a model that takes adsorbate properties, conditions, and MOF properties as input. The difficult part is obtaining a model that can make accurate predictions for adsorbates that were not included during training. During simulations, each adsorbate atom has three parameters that dictate the energy of interaction with the framework atoms and other adsorbates. So we wondered if a neural network could learn well how loading changes with these three parameters. The problem is, models of real adsorbates were developed to reproduce physical reality, not to have a distribution of parameters suitable to train a neural network with. Luckily, in simulations, we can just invent adsorbates whose parameters are not designed to reproduce physical reality, and we can assign these parameters on a grid. Thus, we trained our model on these alchemical adsorbates and tested it on real adsorbates. Briefly, the resulting predictions were highly accurate in multiple MOF databases. Here, predictions are shown on the y-axis and simulations on the x-axis for 6 real adsorbates at 10 pressures or fugacities. We can also accurately predict the shapes of full isotherms. Orange lines are predictions and points are simulated. Our model was very successful for predicting loadings of small molecules. However, we are working on extending our model to adsorption of gas mixtures and to complex adsorbates to further expand its practicality. With that, I would like to thank my fellow lab members, advisors, Mines HPC department, and funding sources from the Air Force, NSF, and Mines.